This lecture is about types and pattern matching in Scala programming. Here we have an implementation of a type list in Scala. We have a trait list with type parameter t and two concrete classes, cons and nil here. The guiding principle behind why we decided to implement these two classes, cons and nil, can be seen from the standard solution in OCaml programming or in functional programming. In functional programming, everybody would define type list with two constructors, nil and cons. Similarly here, we define a trait list and two concrete classes, cons and nil, corresponding to the type data constructors here. And this trait list specifies the type that we want to define. It states that we have to define this is an empty method and two other methods, head and tail. In the case of cons, the two fields, head and tail, are declared with keyword val. So they become public in the Java terminology, which means that they are visible to the outside. So by using the keyword val, we effectively implement these two methods, head and tail. And here we implemented the remaining method is empty. In the case of nil, you can't have a concrete, you cannot return interesting value out of these two methods, head and tail. So we have to throw exceptions. And this is empty always returns true. In Scala, you can easily create a new list with an expression like list 1, 2, 3. This expression creates a new list with the element 1, 2, 3. What happens is this expression automatically expanded to list.apply with arguments 1, 2, 3. So this method apply has a special meaning in Scala language, which is every expression of this form automatically expanded to the first expression, calling its method apply with the second expression as an argument. So therefore, the class that this expression f belongs to should define method apply. And similarly, this expression expanded to expression f calling its method apply with arguments a and b. Here's an example. This is an anonymous function you can declare in Scala. And the Scala compiler automatically expands this anonymous function into this new class, which implements trait function 1. So function 1 is a trait with two type parameters, and it has only one method apply. So you can think of this expression as a syntactic sugar for defining this class, which extends the trait function 1. As a side note, we see a prefix minus here and prefix plus here. So this minus sign indicates that function 1, the first type parameter, is a control variant. And this plus sign means that the function 1, the second type parameter, is a covariant. Now, after creating this anonymous function, we have an expression f of 7. And according to the interpretation of this apply method, this expression automatically expanded to f.apply with argument 7. In the end, we call this function with argument 7. With the apply method in Scala programming, we can easily implement a design pattern called factory pattern. Suppose that you'd like to create a new object of type worker vertex here. And this is the way that you would use factory pattern. And according to the interpretation of this apply method, this expression automatically expanded to worker vertex dot apply with the arguments. So therefore, you have to have an object with this name. So you create a new object for the type worker vertex or class worker vertex. So this is usually called a companion object for class worker vertex. Now, whenever you have an expression of this form for creating worker vertex object, you end up calling the apply method here. So this is the only place where you actually create an instance of this worker vertex. In this way, you can easily implement this factory design pattern in Scala using apply method. In Scala, we have this notion of subtyping and type bounds. To express the subtyping relation between two types, we can use this notation, which says type S is subtype of type T. We can also use this notation, which says this time type S is a supertype of type T, which is equivalent to saying that T is a subtype of S. So here's an example. We define new method with type parameter S and actual argument R. And this actual argument must have a type S. So we effectively implement a particular form of polymorphism. Because you can apply the method to arguments of various types. But at the same time, we'd like to add a new constraint, which is the type S, or the type of the actual argument, must be a subtype of interset. So you can apply the method to many different types, but all these types, the types of the argument, must be a subtype of interset. So essentially, we'd like to set the bound of the argument type, and the bound is going to be interset. In this sense, we implement so-called bounded polymorphism, which is very useful in object-oriented programming. This example states that the type S must be subtype of interset, but it is also supertype of non-empty. So this is also allowed in Scala programming. So to understand the notion of subtyping, we have to have a clear understanding of principle of subtyping. My own interpretation of principle of subtyping is A is a subtype of B if an expression of type A can be used wherever an expression of type B is expected. So here's an example. We have human type, and we have, say, male type and female type. We can say male is a subtype of a human because whenever a human is expected, we can just provide a male. And similarly, female is a subtype of a human because whenever a human is expected, we can provide the female instead. So therefore, female is a subtype of a human. Let's see how Scala supports variance of types. Suppose that we have this subtyping relation, A is a subtype of B. And suppose that we have a class C with some type parameter. We say that this class C is covariant if this subtyping relation holds. So C of A is a subtype of C of B. So direction of this subtyping relation stays the same. In this sense, we say that C is a covariant. If the opposite is the case, that is, C of A is a supertype of C of B, we say that C is a contravariant, in the sense that the direction is now the opposite. If C is neither covariant nor contravariant, we say that C is a non-variant. We use this syntax to declare the covariance or contravariance or non-variance of class C. In order to state C is a covariant, we use this plus symbol as a prefix. And to state that C is a contravariant, we use this minus symbol. If no symbol is provided, then C is declared as non-variant. Let's see an example of a variance of types in Scala. So we have seen the trait function 1, which has two type parameters, t for the argument and new for the return type. And the argument type is declared as a contravariant, and the return type is declared as covariant. And this is precisely the subtyping rule for function types that we learned from the programming language course. So in this subtyping rule, function types are covariant in the return types, but contravariant in the argument types. And this definition of trait function 1 captures precisely the same subtyping relation in function types, covariant in return types, but contravariant in argument types. As an example, let's consider covariant list. If a list is a covariant, it is very useful. Here's an example. Suppose that we have this subtyping relation. Lion is a subtype of animal. And we have a type, list of lion. If list is declared as a covariant, this list lion is automatically converted to list of animal, which is very useful in practice. Now, we'd like to add new method prepend for the list type. This is the first attempt. We declare the trait list with covariant type T, which is the type of its element. And this is the definition of method prepend. It turns out that this code does not compile with the type error. So what this example means is that if you declare a class or trait with a covariant or contravariant type parameter, you have to pay the price by implementing your class or trait so that it remains consistent with the notion of covariance and contravariance. Otherwise, your program does not compile. Let's see why the previous code fails to implement the covariant list. Suppose that we have two types, t and new, for the element of the list. And we have this subtyping relation. If a list was indeed covariant, then we should have this subtyping relation as well. Now, consider the situation described here. We have a list Y of type list U, and we are going to prepend a new element Z of type U. As a result, we would have the same type list of U. Now, according to the principle of subtyping, if we have this subtyping relation, we should be able to substitute X wherever y is used. So currently, y is used here. So with this subtyping relation, we should be able to replace this y with new expression of type list t. So let's replace this one with x without changing anything else. So if list was indeed covariant, we would have this typing relation as well. But currently, this doesn't work. Let's see how we can fix the previous code so that we can recover the covariance of type list. Suppose that we have this subtyping relation for elements of a list. The observation from the previous slide is this one. Suppose that X has a type list of T. Then we should be able to prepend a new element of type U. And the result must be of a type list of U, not list of T. So if you further analyze this observation, it means that if you have a list of type T, then you should be able to prepend an element of type U, which is supertype of T. So here we prepend an element Z, which is a supertype of T. And the result is going to be no longer list of T, but instead list of U. And if you think about this, it makes sense. For example, suppose that you have a list of lion. So you have a list of lion. Now I would like to prepend just an animal. So animal is going to be of type U. So animal is going to be of type U. And once you add this animal, which can be any random animal, then the result must be list of animal, not list of lion, because you have no idea what kind of animal this is. So you cannot claim that the result is still list of lion. So in other words, once you add an animal to an existing list of lion, the result is going to be list of animal. And the implementation here captures this phenomenon precisely. Scala supports case classes and pattern matching, which is perhaps one of the most useful features that you can find in Scala. So here's an example. We define trait expression and implement two case classes, number and sum, extending expression. So here's an example of performing pattern matching on the expression. We use a keyword match and case, just like functional programming. And this example illustrates that to instantiate the case class, you don't need a new keyword. So this number one instantiates case class number and creates a new object. According to the way that Scala expands this form of expression, number one expands to number dot apply dot one. And Scala compiler automatically generates this apply method for you. So you don't need this new keyword, as in new number one. So this is unnecessary. In addition, case classes automatically generate equals method for you. And it turns out that this equals method is extremely hard to implement correctly. So using case classes is a big benefit to programmers because we don't have to implement this equals method ourselves. You can just reuse the equals method provided by Scala compiler for case classes.